On Software Engineering Daily, we do our best to keep up with the evolving Hadoop stack. Stream processing is probably the component of Hadoop with the most variety, and assessing the differences between projects like Flink, Storm, and Spark Streaming is difficult without an agreed-upon set of metrics to compare them. Yahoo's engineering team has created a set of benchmarks to do exactly this. On today's episode, we compare streaming frameworks with Yahoo's Bobby Evans. But first, we're going to take a moment to hear from a sponsor who makes Software Engineering Daily possible. You don't have to settle for a job that makes you unhappy. And you don't have to go through the pain of searching through millions of job listings. Hired.com brings job offers to you, the engineer. Hired is a job marketplace built for the engineers. A few years ago, I was unhappy with my engineering job. I felt stuck, I felt underpaid, I felt alone, and I didn't know my value in the job marketplace. It's a very opaque market. So I used Hired.com to find a new position. Hired connected me with a talent advocate who guided me through the process, like a free concierge. They made me feel valued. It was like a white glove service. And this talent advocate helped me with all the questions I had. Should I ask for more money? Should I consider relocating to try to get a higher salary or a better job? The talent advocate that you get paired with on Hired.com helps you with all these kinds of questions. I got several job offers, and I found one that was a good fit. In fact, engineers who use Hired.com get an average of 5 offers from great companies like Facebook, Uber, and Stripe, and the companies are bidding on you to try to get the best engineers, and so you end up with the higher salary. Go to Hired.com/SEDaily for a $4,000 bonus upon signing up. It is completely free to engineers looking for a job. I've interviewed the founder of Hired, Matt Mitchkovich. He also started 99 Designs and SitePoint. He's a software engineer, and he understands that engineers deserve the leverage in this super competitive market where great engineers are at a premium. Check out Hired.com/SEDaily. I'm happy to advocate Hired to my listeners because it puts power in the hands of engineers. Now let's get on with this show. Stream processing engines have grown in number in recent years, and it can be hard to keep up with which frameworks should be used in which streaming use cases. Bobby Evans is an engineer at Yahoo working on streaming frameworks, mostly on Apache Storm. Bobby, welcome to Software Engineering Daily.
Thank you.
Let's start from a high level. What is the purpose of a streaming computation engine?
So, big data really revolves around having massive amounts of data. And with small amounts of data, you get to answer questions about that data fairly quickly. You either ask lots of questions and can dig into things, or you want to be able to respond to the data very, very quickly. And that's what streaming really is about, is how fast from when the data is first produced to the point that I can respond to it, and trying to reduce that latency. A lot of use cases are around human interactions, and so those latencies are usually on the order of seconds. And so things like Spark and some of the other micro-batch systems tend to be able to deal on the order of seconds, which is fine for human use cases. But there's another class of use cases where you really want much, much lower latency, and this is usually things that are consumed by a machine. Mm-hmm. And so you have a feedback loop. And Storm and Flink really are true streaming engines that they can respond sub-second and be able to really reduce that latency.
And I think one thing that is probably worth pointing out is that when we're talking about streaming, we're usually talking, well, at least as I understand, we're talking about streaming across different machines. We're talking about streaming across a distributed system. Because if you're just talking about your personal machine, most of the operations within a single machine would be considered streaming operations, I think. But in a streaming computation engine is generally handling events across a distributed system. Would you say that's accurate?
Yeah. You can handle streaming with a single machine, but that's an easy use case. That's not that exciting. It's when the data is so big or is coming at you so quickly that a single machine just can't handle it.
Right.
If your data fits on a single machine, do it on a single machine. That's where it should be. Don't bother with Hadoop, don't bother with Spark, any of these things. It's going to waste your time and be slower.
Mm-hmm. So we've had batch processing systems in the Hadoop distributed system space for much longer than we've had effective streaming computation. And I want to quickly outline the difference between these two types of systems and the gradient that exists between the batch and the streaming area, and make sure I have the definitions correct. So in a batch processing system, which is how these early Hadoop distributed systems were built, you often have data that gets accumulated in some centralized repository like an HDFS, Hadoop distributed file system, and maybe once every day, like every night, you have a job that processes all the events that have run throughout the day. But the desire with these streaming systems is you want to actually get to a situation where instead of just processing all the events on a 24-hour interval or a 12-hour interval or whatever Hadoop batch interval you have, you instead get into a situation where you have this streaming engine that's always running, it's always ready to process a new event and update the overall system to ingest that new event such that the system is aware of that event on a much lower latency timescale. Would you say that's an accurate explanation?
Yeah, that's fairly accurate. That it kind of goes back to SLAs again. How fast from when the data arrives do I need to be able to respond to it? And Yahoo, lots of other companies have built streaming systems based off of batch. That the data arrives, it's aggregated, and I know for Yahoo at least, we were doing 5-minute file aggregations. And so every 5 minutes, a new job would come up, it would process that data. Then there would be other roll-ups that were like 15 minutes, hourly, daily, weekly, monthly. It's how much data are you willing to batch before the overhead of running that Hadoop job or the Spark job or whatever else becomes too much that it's not worth it anymore.
Got it.
So with streaming, that's like you said, we process an event at a time. We never take that concept of there's a batch, I'm going to process all of this data at once. It's every single event shows up and is processed independently.
Got it. So you are part of a blog post called Benchmarking Streaming Computation Engines at Yahoo. What was the motivation for writing that blog post?
Sure. So I want to start off by saying benchmarks are all crap, but there are some benchmarks that are better than others. I'm an architect at Yahoo. I own several different projects. Kafka, Storm, and Spark are the ones that I'm primarily responsible for. And we provide them as a service to other teams within Yahoo to be able to use. So looking at Storm, we started doing Storm several years ago, before most of the other streaming engines had really taken off. And it's been years. We wanted to see how well Storm performed in real-world use cases compared to other systems. So we went out and we looked at a number of benchmarks that other people had done. And like I said, all benchmarks are crap, but a lot of the other ones had even bigger, more serious flaws than the one we have. And they were doing the kind of micro benchmarks. So things like how fast can I process data and I can read the data and do nothing with it? How fast can I do a distributed grep where I read in the data, I look for a specific substring, and throw everything else away? These are okay pieces that build up, that can be used to build up more of a holistic system. But looking at them independently, especially in streaming, is very, very hard. Because you really care about the throughput versus the latency. That I have a given throughput that I have to be able to handle. How many machines is it that I'm going to need? How much money do I have to pay to Amazon or whoever else to be able to handle that throughput at a latency that is going to meet my needs?
Right. So most comparisons of streaming computation engines, they don't take the time, or they don't get this test of a holistic test against an entire systemic use case. They don't test against a real world use case. And you've kind of explained that they, maybe take this piecemeal approach that maybe doesn't exactly capture the holisticism that you need to understand the system. We did a show with Satish Mittal, who is from a company in India called InMobi, which it's an advertising company. Mm-hmm. And he talked about that show was actually about evaluating different streaming computation engines, but I don't think it was from the standpoint of, here's a benchmark we designed and we tested it against we tested the different systems implementing these different benchmarks. It was more of like a theoretical exploration, a research exploration. Why is the approach of benchmarking, of experimentation, preferable, or what are the trade-offs between that approach and the research-based approach?
For me, it's because I'm not smart enough to take everything into account that might happen in the real world. The real world is a messy place. And so for us, when we see things running in production, because we do this a lot, we see odd things happen, like a top of rack switch will get saturated because we scheduled things badly, or a two different processes running together that they'll interfere with each other in really strange ways, not necessarily through the CPU, but possibly through the cache or other things. And you want to be able to pin these processes to a given CPU or whatever to get optimal performance. And taking these things into account is very, very hard to do theoretically. At a very high level, you can look at the different approaches theoretically and say, in general, this approach is going to have lower latency versus that approach, which is going to have better throughput or whatever else. But being able to take these things and put them in a real-world use case lets you know how it's going to perform for that use case, what you really want to do. And that's why benchmarks, like I said at the beginning, really suck, is that they aren't your use case. They aren't doing what you actually want to do. And until you try it out, there's still that uncertainty. You just don't know. And so having a real-world benchmark gets us a step closer in saying, this is something that looks more like reality, but it still isn't the same thing as taking your code, running it on this system, and seeing how it performs.
This comes back to the distributed systems enumeration that I wanted to give at the beginning, because in a distributed system, the philosophy around distributed systems is all about these Byzantine failures where you just have these unexpected things that happen that you almost you admit up front, we can't predict all the different failure cases. And I like the idea of experimentation within a distributed system because it's almost like admitting we need to run these tests in order to see the unknown unknowns. Yeah. So before we get into talking about the actual benchmarking that you ran on these different systems, I want to talk about at a little lower level of granularity, what are the commonalities between these different systems? So we've got Storm, Spark Streaming, Samza, Flink, all these other streaming platforms. There's so many of them. What are the set of requirements that every stream processing framework fulfills to some degree?
Well, so that gets back to what was your definition of stream processing and streaming. Some of these systems, by the definition of an event at a time, are not actual stream processing systems. Spark, for example, Spark Streaming is a micro-batch system, that they take that original concept of doing a batch of data and they condense it down as small as they possibly can. And so on the order of a couple second size batches. And so you get a second or 2 seconds or 5 or 10 seconds of batches. And they then have put a very nice layer on top of it that looks like a streaming system layer, where they say, here are the processes I want to do that look kind of event by event, and make sure they're idempotent and process the data this way, but the reality is it's still flowing through as a batch, and there are controls at a higher level around all those batches. Whereas you compare that to Flink or Storm, in those cases, it truly is event by event. An event comes in, it's up to either the operating system or the framework itself to decide who's going to process that event, give it CPU resources to be able to process that data, send it off to some other thread or some other piece of code to be able to finish processing it and hand it off in that way. And so, in theory, there really isn't that much of a difference between the two, but for the most part, at a conceptual level, streaming is just providing an API to users that says the set of data that you're processing is not a single file. It's not a small piece of data. This is an unbounded set of data. And whether we batch it behind the scenes for you to be able to give you better throughput or not, it's really the realization that data doesn't end. That people looking at your web page, interacting with your app on the phone, whatever it is, that flow of data never stops. It continues constantly, and providing a framework that abstracts that away from the user.
Right. So that describes the similarities. And before we get into benchmarks, now I'd like to talk a little bit about the differences. So you touched on this micro batch idea that Spark works within, and we'll get into more about the consequences of this. But what are some other trade-offs? What are some other different axes or dimensions that these frameworks are trading off between that will help us understand why there are so many of them?
A lot of them are different use cases. And so people have different desires on how they do processing and what they're trying to process. And so distributed systems are hard. By definition, the bad things happen. You have to deal with failures. How do you deal with failures? The easiest way is to just ignore them and say, I've lost some data, whatever, who cares? And so there are some use cases that's okay with, that you're doing kind of just a rough guess as to what it is. You're doing some statistics around these numbers. You're not putting actual money on the line necessarily, or being able to, it costs more in the compute power than it's worth to get exactly once processing. And so you can have something where you say, if I lose data, I don't care. There are other ones where you say, I want to make sure I processed all my data, and if I double count things, that's okay, but I want to be absolutely positive I processed everything. And then the final one is, I want to be like Hadoop. I want to know that I processed every single event once and only once throughout the entire system. And so a lot of the differences around these different systems are in how they handle those different situations. I processed it. Best effort processing, that's easy. There really is no difference between the systems. But there are different ways in how they handle the coordination of exactly once processing, or getting closer to exactly once that at least once processing. Okay. And so with Spark and its batch processing, it's already set up for exactly once. It tracks everything at the batch level. It makes sure that the batch was fully processed and committed to wherever the output is, following the same Hadoop output formats. And that makes Spark very easy because it is an exactly once processing system. They didn't have to redo anything around that. But then you have other things like Apache Apex and Flink, where they essentially send out control messages and they have periodic checkpoints. So every single processing step that you can send your data to, that is going to take an event and say filter on that event or augment it with something else or whatever, if that has state in it, they will checkpoint that state periodically along with information about how many events or which events have been fully processed, and then do a handoff scheme where they talk to each other. The different pieces communicate back and forth with each other until they're positive all of the data has been processed, either at least once, or if bad things happen, then they can roll back the state and try again. And that's one way that they deal with it, the exactly ones.
Okay.
For Storm takes kind of a separate approach where it's kind of a hybrid between the two.
Okay, great. Well, so we'll explore those differences a little more. I want to get into the benchmark discussion so we can get a prototypical use case to circle our discussion around. So there's a prototypical example application that you decided to use for this benchmark, which is this real world example of the advertising application. And this is like a really common use case. It's really important. You have several advertising campaigns. You have a number of ads for each campaign. You've got high throughput. Explain why this is a good sample use case for a benchmark.
So we picked this use case primarily because it's something that we're familiar with. We have lots of people that are our customers at Yahoo that do this exact same thing, that they will process data in. This is a very simplified form of it, but it's essentially counting how many times something was seen, counting who saw this particular ad, how they interacted with the ad, things like that, so that you can target it better to make sure that this type of ad is interesting to this type of individual so that we can do better targeting towards showing ads that people care about, or B, a use case that I really like was just simply counting how many times the ad was shown so that we don't overspend. If as an advertiser, they come in, they say, I want to spend $100 on showing this ad. Well, I want to make sure as a publisher that I show exactly $100 worth. Because if I go over, I gave them free views and I can't charge them for that. If I go under, I can't charge them for what I haven't shown. And so having a feedback loop, especially when you get close to the end of that campaign, really becomes important to make sure you can hit the nail right on the head. And that's a fairly simple amount of math, but doing it at scale can be very, very difficult.
Yeah, and if people think, maybe it's advertising that sounds frivolous, it's certainly something that is analogous to all these other kinds of streaming applications you could have, whether it's like a Hadron Collider or, reading data in space or all these, if you're reading real-time data in a car or something, all these things have very similar situations where the data pipeline is gigantic, but the mathematics behind it are somewhat simple. And you just have this set of operations you need to do. So that said, there is this set of operations that you said were basically the benchmark. You had you wanted to do this set of different things and test it on each framework with some given amount of throughput. So explain the operations that each framework was going to have to provide and at what throughput level. Like give me an idea of the parameters that you were going to use for each benchmark on a streaming framework.
Yeah, so I want to start out by saying that our numbers and everything were very preliminary. We wanted to get them out, but it's not completely done at this point. What we started out by doing was simply saying, well, that we wanted this basic use case, and we want to expand the use cases in the future because there are lots of other use cases, like the Large Hadron Collider. We've talked to people about that. That's a very mathematically, computationally intensive system, and so they're trying to figure out what data to throw away, and because the disks can't keep up with the amount of data they produce. So there are very, very different use cases. So don't take the advertising use case and assume it's going to apply to the Hadron Collider or anything like that. But
it's the base case.
It's the base case. So the base case for the advertising is that we take an event that came directly from, say, an ad server. Oftentimes, this is very compressed data. They don't include very much with it because you don't want to have this extra data in the URL or whatever else. It's mostly just an ID that is identifying this particular ad was shown to this particular user. You get those two pieces. But in order to do something interesting with it, like look at an advertising campaign or other things, you need to augment that data. And that data is usually stored in an external database. And so the first thing you do is you'll take that ad ID and that event and you'll augment it with extra data. You'll look up things about the ad, the campaign, the other things associated with that, and then you'll look up things about the user and try and find all the pieces of information that are relevant about those two pieces. Well, sorry, I forgot the first step. The first step is filter out the events that we don't care about. In this particular use case, we had extra events of things that are likely coming in from the ad server, but at least for this use case, we don't care about. Once they've been filtered, we'll go in and we'll augment the data to be able to have the pieces of information we care about. We'll throw away a few pieces of information that were part of that beacon that we don't care about and send them on to do some aggregations. And then the aggregations are actually very simple. We're simply bucketizing the data and aggregating counts over a specific range of time, trying to see how many times this ad was shown in this situation.
Right. And so to clarify, you implemented this benchmark within each system. So in the different systems you were evaluating were Flink, Spark Streaming, and Storm. If I'm correct, it was just those three. Is that correct?
So,
okay.
So what we did is we set up two pieces. One is a common piece where there's a Kafka. So Kafka is a streaming state store. You put events into it, you can read the events back out of it in a streaming way. So it's kind of similar to HDFS, but different because it's not in files. It's kind of like you're tailing the end of a file as things get written into it. And so we picked that one because that seems to be where most everybody is coalescing. There are a few other ones that people use, but a lot of people seem to really fall around Kafka. And then we set up a Redis instance just because it's very fast and performant to be able to act as the database. We could have set up HBase or some other NoSQL store. It was just we wanted something to be able to be there. And so we wrote some code to be able to publish data to Kafka for these to be processed, to populate that database. And then we also have a piece of code to check the correctness of the result when everything's done. And that is independent of whatever streaming system is using this. The goal here was to be able to have an external piece that the streaming system is a black box, so that we can be positive that it's doing the right thing and then also get the right performance numbers out no matter what the system is. Mm-hmm. Some of these systems have much better monitoring and built in than other systems do. And so we wanted to be able to collect the metrics independent of whatever that system was.
Okay.
And then we implemented each of those things in Spark, Storm, Flink. We've had a few pull requests for other systems since then, but yes, those were the three we picked to start out with.
I love being a software engineer because of how easy it is to build side projects, and I've built countless side projects. I've built a social gambling application, a dating website backend that had 0 users, stock trading music rhythm application for Android. And I think every developer should have side projects. So when I have a web app that I want to deploy and share, I want to show my friends my most recent project that nobody will care about, I use DigitalOcean to quickly spin up a server and host my projects. And who knows, if one day one of my apps takes off and goes viral and people actually do care, I can easily scale using DigitalOcean's flexible pricing plan. Companies like TaskRabbit that have grown rapidly have used DigitalOcean for this very reason. But until this happens, I will happily stick with the $5 a month plan. Sign up with promo code SEDaily to get a free $10 credit as a listener of our show and start building your apps. We would love to see what listeners build, so send us an email showing us your project. I've also interviewed Moise Uretsky, who is the co-founder of DigitalOcean, and he mentioned that the ease of use and the flexibility is why they built the service in the first place. That DigitalOcean interview is one of my favorite episodes. Moise talks about bleeding in a data center. He says, you don't know how hard it is to do a cloud hosting service until you've bled in a data center. It's really interesting. So speaking of which, let's get on with this episode of Software Engineering Daily. So what were the bottlenecks that you expected in this pipeline of operations? What did you expect to be the most time-consuming or processor-intensive computation along this benchmark pipeline?
Well, none of them are actually computationally intensive. That's the thing. It's all very, very simple computation. There's a string compare and just throwing some pieces out. There's a quick database lookup. There is some aggregations, essentially summation, and then writing the result back out to a database. So they're very simple operations. And part of the goal with this was to see how much of the overhead. I mean, this is fairly common. The most of the computation we do is very simple computation, and so the overhead of the system seems to dominate in a lot of these use cases. But I wanted to see in a real world use case that wasn't word count, but was similar to word count, how much did the system actually dominate? And that was one of the things I was really curious on.
So, correct me if I'm wrong. So, as I understand what you just said, the actual operations of what the frameworks had to do, not very complicated. The bottlenecks that you expected to emerge were they at the points of integration, like the point of integration between a streaming framework and Kafka, or the streaming framework and the database, or
the streaming framework itself?
Oh, okay.
That most of these systems, because they're distributed, they have to communicate between at least separate processes on the same box, but typically also separate boxes. And so the use case of how fast can I read data and throw it away is actually a very valid use case, because it's measuring what that overhead is. That was one of the first benchmarks we wrote when we were evaluating Storm, was the speed of light test. How fast can I do nothing? To kind of measure an overhead of the system itself. But you are trying to do things, and when you're doing everything on an event-by-event basis, very small amounts of computation can add up very quickly. And so I wanted to see how much that overhead was and how that compared between these different systems.
So I'm still not clear, because I thought that the distributed elements, like the coordination between different processes across different boxes, I thought that was kind of like standardized on Zookeeper, and Zookeeper just takes care of all that, and you don't even need to bat an eye. So I guess I'm totally mistaken about that.
So for example, with Spark streaming is doing microbatch behind the scenes, and by far the bottleneck in Spark streaming for us was the overhead of processing a batch in the scheduler. That as we tried to get the batches smaller and smaller to get the latency better, the computation involved within the scheduler just became more and more and more, to the point that actually refreshing the UI slowed down the processing, because the batches were just so absolutely tiny to try and get sub-second latencies. We just couldn't do it. And so we increased the batch size to the point that it could keep up and it was doing things well, but the latency was much, much, much higher than the other systems. Whereas in like Storm, I had just finished doing a bunch of benchmarking and performance improvements to try and improve the throughput there. And previously, the vast majority of the overhead was actually within context switching. That because we're processing everything event by event, an event would come in, a thread would wake up, it would process that event, it would be done with it, hand it off to another thread, and the amount of context switching, the overhead in the OS to be able to switch back and forth between making a thread sleep and making another one wake up, was the thing that dominated by far. That I was able to more than double the throughput and still reduce the latency by playing around with batching and other things to be able to stop that extra overhead within the operating system. And so you get very similar things also with the network. That's why on HPC systems, the supercomputers, they actually bypass the operating system and even the CPU in many cases to be able to do communication. That's what RDMA is all about. It's remote direct memory access. And so the network card is tied directly into the memory. It can do a DMA access from another box on another piece of the network and shove that data directly over to where it needs to be without the OS being involved at all. And the OS is doing all kinds of things that are important that keep us safe from viruses and other things that want to steal that data or behave badly, but it also slows things down drastically.
Okay, so you said a lot of interesting stuff there, and I want to delve into one specific thing. So, kind of getting back to a basic conversation of this benchmark and the comparison between different frameworks. You mentioned a comparison between Spark and Storm there, and I'd like to kind of roll back to a little simpler level of the conversation. How did the implementations of this advertising benchmark differ between how you implemented it in Storm and how you implemented it in Spark Streaming?
Yeah, so really the big difference was around the database access. That in Storm and in Flink, because the processes, the bolts and spouts or functions or whatever, they're long-lived, we're able to create a connection to the database, leave it up, and just stream things through. We had to make sure that those processing was idempotent so that if we did it multiple times, especially for Flink, it wouldn't matter. And so for a read, that's not a big deal. For the write, that's where things got a little bit hairy, but it really wasn't that bad because we weren't looking for exactly once processing. And so we kind of punted on that. For Spark is doing microbatch, and so it becomes a little bit hairier with how they do that. And so the game we played was to be able to use a function that processes the entire batch and to establish the connection at that point for Redis. And so we'd establish a connection to Redis, process the entire microbatch, and then we'd have to reestablish it. Simply because of how Spark works, it could have scheduled that one bit of processing on a completely different host the next time. And so caching that connection really is difficult. Mm. But on the final output, if we were going to do things truly the proper way with Spark, we would have had to have written a Hadoop output format that could write into Redis. And that was a bit more complicated than we wanted to deal with. And so we kind of punted on it, and it's a bit of a hack the way we did it. But we essentially wrote another processing element that would write the data into Redis, but it wasn't, and we forced it to run. And so it wasn't a true output format. It wasn't doing things truly the right way. But with Spark, it's essentially you get exactly once processing only. There's no way to turn it down. And so that was really the big difference, was just being able to understand how those different systems handled the failure cases so we could communicate with the database in an actual efficient way.
Mm. And so one of the consequences of the way that Spark works cropped up in the results of your benchmarking, and that was that with high enough throughput, the 100,000 messages per second, for example, you said Spark was not able to keep up, and you had some modifications, and you touched on this a little bit earlier, but could you just clarify why couldn't Spark keep up, and what were the alterations that you made in order to allow Spark to keep up?
So, again, that was going back to what I talked about before, is with the scheduling. That when the batch size is very, very small, then you get very low latency. But you also have a set amount of overhead around each batch. And so the bottleneck very much was not in the processing of the data, but in the scheduling of all those batches. Mm. And so as the throughput increased, the batches on a per time basis, we didn't dig into the exact details of exactly what was going on. So I can't answer why, as the throughput increased, it really did start to slow things down. That's something we'd like to look into more, but increasing the batch size increased the efficiency of being able to do those processing, the shuffles and everything else associated with it. And So as we were going along, we hit a point where we couldn't process the data fast enough. We were falling behind. So we increased the batch size and we're able to go on. And so you get kind of a bit of a stair-step pattern in the latencies.
Yes. And you also increased parallelism. Can you talk about that?
So we experimented with increasing parallelism. So there are a number of different optimizations that these different streaming systems can do. And like I said, where Storm had a lot of problems with context switching, where it would hand the data from one thread to another thread to another thread, Flink and Spark try to avoid this, and Storm in some cases, by taking these different processing and having them happen sequentially, serially, on a single thread. And so by default, most of these systems will look at the parallelism of Kafka, because Kafka itself is a distributed system, and they will allocate as many threads as there are threads in Kafka, different disks in Kafka that the data is being written to. And so we tried increasing the parallelism within Spark to be able to be more than the number of threads in Kafka, but that actually had a negative impact, simply because we weren't CPU bound within the actual processing itself. It was the overhead of the scheduling, and increasing the parallelism added extra overhead because data had to be sent off to other machines, and also because the scheduling became more complex.
Okay, I understand. So we've delved into Spark. We've touched a little bit on Storm. We haven't really talked too much about Flink, except tangentially. So let's talk about Flink a little bit. What is the big draw of Apache Flink, and what are the features that you get from Apache Flink that you don't get from Spark Streaming or Storm?
So Flink is kind of positioning itself as a stream processing system that can also do batch. Because if you think about it, batch is a subset of stream. It's just simply the stream ends at some point, so you're done. And I hadn't done much with Flink prior to the benchmark. We were very curious about it. It's getting a whole lot of buzz. And we wanted to evaluate whether Storm was anywhere in the ballpark compared to what Flink can do. And if not, what steps we needed to take to be able to get there. Or if it was just way off, what steps we need to take to move to Flink. Because we're here to provide a streaming service. We're not here to provide Storm. We're here to provide streaming to Yahoo. Sure. And so I really wanted to know what was happening. And so Flink, from our experiments, really provided a very nice middle ground. That we hadn't done anything with batch, and so as far as how well it actually performs in batch is up to you to evaluate. But from what I've read, it seems to perform very, very well. And from the streaming side of things, it seemed to be able to keep up very closely with Storm as far as the latency and to be able to provide very similar throughput. And so it definitely seemed like a very nice solution. But again, we haven't finished with our benchmarking. One of the things we really want to do is to go towards a much bigger cluster with much more processing going on, because we provide a hosted multi-tenant cluster to our users. And so our clusters are an order of magnitude larger than what we tested with. And so we wanted to be able to see how these things handle when there are multiple racks, multiple different pieces that are involved there. So Flink is definitely an interesting thing. I don't think it's quite as mature as Storm is, especially from an enterprise standpoint with security and other things at this point. But it's definitely a very interesting technology.
Sure. Okay. So, but talking more about the idea of, so as you said, Flink looks at batch as a subset of streaming, whereas Spark looks at streaming as a subset of batch. I think I got that correct. What is Storm's point of view on this? And if you want, so I think you kind of touched on the crucial advantage of Flink is that it sounds like you can write your batch jobs and your streaming jobs and get performance out of Flink that leverages the fact that the system understands that you're in a batch mode versus a streaming mode. Is that correct? Is that accurate?
Yeah.
Okay.
I don't know exactly all the details of the internals of Flink, but yes, that's what they're trying to do.
Okay, so what is Storm's perspective on this, and how does, why can't Storm take advantage of the fact that it's, in a given situation it says, oh, I'm in a batch processing mode, I can leverage that knowledge?
We could. Storm definitely could, but Storm does not provide a batch processing API.
Oh, okay.
Storm was written to be a stream processing system. We haven't extended it to be able to do batch, and quite honestly, I don't really see that much of a need to, at least at this point. They're all open source projects, so as the community gets new ideas and decides to go in new directions, that's perfectly fine. That's what they do. But from my standpoint and what I want to do, I want to add in features to Storm that are really specific to stream processing and can make it the best stream processing system out there. So, for example, Hadoop has this concept of a distributed cache, and where you can take arbitrary files, ship them off to all the different nodes, and then your map or reduce job or whatever else can take advantage of those. They can open up the files, use them for something. And this is really common in, say, doing a map side join. So if you want to do a big join that's distributed, you can either do the shuffle, which is expensive, or you can ship a very small amount of data to every single mapper and have it look it up in that table as the join streams through. Storm can do very similar things, but when we added in the distributed cache feature, we put in some extensions that are streaming specific. So I can update that data on the fly without ever having to tear down what was there. And so for me, with Storm, if I can concentrate on what makes stream processing great without having to sacrifice something that, if there's a trade-off between batch and streaming, I don't have to make that trade-off. It's a streaming-only system. Now, that's not necessarily great for all users. There are lots of people who have a use case where they want to process some massive amount of data and then use that as part of their stream processing. And so if you don't have batch with that, it's more complicated because now I have to deal with two separate systems to be able to unify those.
So is batch something that is, are we always going to want to do some form of batch processing on our big data systems, or is this like a relic of the past that we're eventually going to move beyond?
So it kind of goes back to that very beginning question of what is streaming and what is batch. For me, there are two different pieces of latency that people care about. One is the latency of how long it takes for me to get a question answered. And so this is why there's Impala. This is why there are all those other wonderful analytics systems like Druid and everything else. I have a set piece of data, and I want to ask lots and lots of questions and dig into that data. It doesn't matter that much if the data is a few days old. I'm trying to, as a human, dig into that data and find patterns or find something that actually makes sense. And machine learning is one of those. At least most machine learning algorithms tend to fall into that case too. How much can I load up a large piece of data and do massive numbers of queries on that data, and how fast can I get those queries back? Whereas the other use case is, I know what I'm looking for. I know exactly what I'm looking for, but I need to respond to that data very, very quickly. And so I see those two different use cases as being very separate. You can get very similar things out of optimizing both of them, because both of them are, some data shows up, I want to go very quickly, whether that data is the query or whether that data is the actual data you're doing. You get some very similar things between those two, but they are very distinct use cases.
So, okay, we've bounced through this discussion of these different systems. I'd like to get an idea of what the conclusions that you took away from this benchmarking exercise were.
So the first conclusion was that Storm is actually doing fairly well. that I was a bit nervous about that just because it is several years old. Flink has been getting all kinds of press, and Storm beat Flink in latency, which I was quite happy with. The other thing that I took away is that my performance optimizations, which did amazing things on word count, were actually kind of crappy on a real-world use case. That we ran both prior to my performance optimizations and then after my performance optimizations, and I did all kinds of things that, when I ran with word count, more than doubled the amount of throughput and dropped the latency. And the throughput on this particular use case did not go up one lick. The latency did drop slightly, and that was good. But the actual throughput, that was one of my goals, didn't actually make much of a difference. Which is another reason why benchmarks are great, because I optimized the wrong thing, apparently. I spent a bunch of time on word count, got it to run really, really well, and, well, now word count, you can go very fast with Storm, but you can't do necessarily, it didn't hurt things by any means, but it wasn't necessarily the best use of my time. The other thing that we looked at really kind of just showed that it was kind of what we expected. We expected Flink to be fast because it was a streaming system, and we expected Spark to have lower latencies but have decent throughput, and that was what we saw.
Yeah, I find it funny that it's like, you create this benchmark and it's just like as controlled an experiment as you can have, and it's still got all these kind of caveats and like, did we actually accomplish what we wanted to, and additional questions raised at the end of it. Maybe says something about the nature of distributed systems.
And tuning those systems too. All of these, we tried to run them with the out-of-the-box configuration. And since then, Data Artisans, which runs Flink, has given us a pull request to try and improve the performance and drop the latency a little bit. We've talked with people in Spark that say that things were off and not really what we wanted, what they would have liked preferably. And so there are all kinds of these small little things that you can tweak and get much better performance potentially out of. But as a normal user who doesn't dive in depthly into distributed systems and become an expert in these things, out of the box felt like the best way to start out with.
So Storm was kind of it seemed like the winner in this situation. Probably had the best results. Yahoo has a lot of experience working with Storm. Is there any chance that the positive results from Storm were due to implementation expertise and an understanding of how the system works?
Of course. I was not being... I wanted to be absolutely sure in the blog post that this is not an unbiased study. that we tried to do things in a very unbiased way, but these things will creep in. And so that's why we released it as open source. We really want people to give us feedback because we're not the experts in absolutely everything. We know Spark really well. We know Storm really well. Flink was new to us. We want to explore all those other systems like Samza and Apex and whatever else that might be out there. But we don't have the expertise or the time to be able to do all of that.
Yeah. I don't think you're ever going to get a job as a experimenter at a pharmaceutical company because you're pretty honest with your latent biases.
I have friends who have done that. It's not that different, actually. They'll throw 4 different things in a test tube, see if it kills the bacteria, and if so, they'll try each of them individually because they don't have time to try all 4 individually. And so it's a real crapshoot, as far as I understand.
Yeah. Interesting. So what's been the response from the different open source communities for these different projects since you published the findings?
I think it's been fairly positive. I haven't heard much from Spark, as you might expect. Flink has actually touted it a fair amount. I've seen them retweet things quite a bit. We've gotten feedback from both communities, though, on how to tune the systems. Apache Apex, some people from that community came over and offered to give us a or to help develop a version of the benchmark for that. And so I think it's been very good. I hope it continues. And we plan to keep it up, that as new versions of these tools are released, we want to be able to keep running it and seeing how things change.
So this lack of attention from the Spark community, I mean, as I understand, Spark is kind of more, at least from like a fundamental use case perspective, it's more for the data scientist who needs to load a working set into memory and then do these different operations on a working set, which seems somewhat orthogonal to a streaming methodology.
Yeah.
Would you say that's correct?
Yeah, that's how we use it at Yahoo. That we'll do machine learning with it. We'll do a lot of exploration with it. Some ETL, extract, transform, link type processing, load processing, but not nothing on the streaming side. We've had a few people play around with it for streaming, but not that much.
And is that kind of because, well, so is there a reframing that that may need to take place for Spark streaming to kind of fit both those use cases, or do you get the sense that Spark streaming is trying to fit a square peg in a round hole, or are there kinds of synergies that you could see emerging from the way that Spark does things to have a good use case for Spark streaming?
It's all about the latency you need. And so, like I said, if you're doing something where your latency can be 10 seconds, Spark streaming is a fabulous solution, especially if you're using Spark already. You don't have to learn something new. You don't have to deploy something new. It works really well at 10, 20-second latencies. If you need something that's sub-second, Spark is not going to be able to handle it. Now, that's in its current form. I know a lot of people at Databricks and at Cloudera and at MapR and at other places that are throwing, look at IBM and how many people they're throwing at Spark. If they really want to get to the point that they have these sub-second latencies, architecturally it's going to be very difficult to do with what they have right now, but you throw enough smart people at it, I'm sure they can come up with something. And so, don't count them out by any means, but yeah. I don't know how much of their bread and butter comes from that at this point either.
Okay, super interesting. So I want to close off with one final question. How will the world of streaming frameworks evolve going into the future?
I think a lot of it is around ease of use and adding in some new concepts natively. So Google has been doing stream processing for a very long time. And you look at their Cloud Data Flow API, you can tell from that they have really thought through how the stream processing should work. One of the really difficult pieces with stream processing is late data. That in the real world, all your data is coming in a batch, but the first event to arrive was not necessarily the first event produced because things happen out of order. And so being able to get really, truly good, accurate results in a very fast way that deals with this out-of-order data is a difficult problem. Flink has been trying to tackle that. Storm has been trying to tackle that. Spark has been trying to tackle that. I think that's kind of one of the very interesting pieces that we all have to grow up a little in our APIs and tackle head-on. After that, a lot of it is around maturity. In all distributed systems, getting visibility into what's going on is very difficult. In batch, you always have if something goes wrong, it's not the end of the world because I can rerun it on another machine, or I can just wait until that batch is done and try again the next time. You have these very defined computations. But in true stream processing systems like Storm and Apex and Flink, you don't get that. That piece is still long-lived. It's not going away at any point. And so you have to be absolutely positive that the scheduling was right. If you want to have very good performance, you have to be able to get really good visibility into what's happening at that point. And that can be a very expensive situation. At Yahoo, I like to say that we have a big metadata problem. That one of our biggest problems is dealing with logs and what logs we keep, what logs we throw away. Lots of people, when they're debugging something, want to log every single event that came in. On MapReduce, you can kind of do that. It writes to the local disk, and then it can get aggregated, and you can look at it. With stream processing, that never ends. How much of that data do I keep? How do I provide people good visibility into that? It becomes very difficult to be able to deal with all of that and provide that in a good, clean way. And so I think there's a lot of maturity that needs to come simply from the enterprise standpoint for debuggability, maintainability, security, all kinds of things around that.
Cool. Well, that sounds like a great conclusion. Bobby Evans, thanks for coming on to Software Engineering Daily. It's been great talking to you. I really like that blog post. And, if you guys have any other interesting findings in the future, feel free to come back on.
Okay.